Thanks for turning to this video where I'll have the opportunity to expand a little bit more on the health effects of radon on humans. And I'd like to begin here with EPA's map of radon zones, which we have seen the Pennsylvania portion of before. But I want you to note that there's a wide swath of problem areas in the U.S. You'll see the reddish area, which is the worst cases. That is, the average radon concentrations in homes is expected to come out above or equal to 4 picocuries per liter. And you'll notice there's quite a bit of red here and in here, and it sweeps through Pennsylvania and up into northern Maine. And so it's a pretty broad area. And I don't want you to forget that even in these yellow areas, which are the least severe areas, such as here in Texas and down in parts of Florida, etc., that doesn't mean that there won't be homes there with high radon concentrations. There will be, I can assure you of that. And so I want to reiterate, before going any further, that the only way to know if you've got a radon problem in a home or building is to test for it. But this shows you the pervasiveness of the radon problem. Now, initially, when we started preparing this video, I was researching into the different scientific agencies that recognize radon as a health risk, and I started making a list that you see here: the EPA, the Surgeon General, the American Lung Association, et cetera, and we stopped making the list because every scientific agency that's reputable is in agreement that radon is a significant health risk. In order to get a handle on the impacts of radon, we need to know a little bit about the radon atom itself. First of all, it's a radioactive gas, and that's what makes it difficult. If it weren't radioactive, if it were inert, stable, then it wouldn't be a problem. But because it is radioactive, it is a problem. And recognize that you can't see it with your own senses. So it's colorless, odorless, tasteless, as you see here on this table. And it's widely prevalent in soil and rock. I know of no place where, let me make that positive. Any place you look, if you drill down into the ground a few feet, put a radon detector down there, you will detect radon. It is pervasive. Now, there's no question, some areas have more radon than other areas. And when it decays, it's going to produce other radioactive elements. Now, a radioactive atom, it might be just sitting here for the moment, and then when it decays, what it does is it gives off little particles. And what's left behind is another atom. And that other atom oftentimes is also radioactive. And it too can decay, leaving behind another radioactive atom. And this might go down for 10, 15, 20 stages. And those residual atoms, each one can produce a health risk to humans. And they are called the progeny. Used to be called the daughters, but now they're called the progeny, the radon progeny. So when I talk about the health risk due to radon, I'm also talking about the health risk due to the daughter products as well. It's just easier to talk about just the radon. And of course, it can have high concentrations indoors, as I list here. If you watched the earlier video, you recognize that there are homes with radon concentrations in the thousands of picocuries per liter. Those are incredibly high values. Let me just discuss what radioactivity is, and you can see here I've drawn an atom, and this has a central region in here, which is often called the nucleus, and the electrons on the outer perimeter of that, actually quite a distance away from the nucleus, but they're listed here. And the electrons really have no impact on us due to radioactivity. The radioactivity, comes from the nucleus. That is an issue for us. And you'll notice I've indicated here, or at least is indicated in the drawing, some of them are shut off. They're relatively large. They're called alpha particles. Others are called beta particles. And a third one is called gammas. In some cases, there are other kinds of bullets shot off by a nucleus, but we'll be concerned only with the alphas, betas, and gammas, actually. And it turns out alpha is the big health risk. So you get a sense here of what's going on. When the atom decays, it will emit some particles, alphas, betas, and gammas, and what's left behind is a residual atom, which may also be radioactive. And I want to make a distinction now a little bit more clear about radioactivity and not radioactivity. So let's suppose that I have this liter bottle here, and let's suppose I have this filled with hydrogen. And imagine for a moment I've put 1,000 hydrogen atoms in here, and I put it on my desk, and I come back to it a month later. There's still going to be 1,000 hydrogen atoms in there. The number of hydrogen atoms is not going to change. But if I put a radioactive atom in here, let's say 1,000 radioactive atoms, and I come back a month later, there will be fewer of those radioactive atoms than 1,000. Some of them will have decayed. And so you'll have maybe 990 radioactive atoms of the first type and 10 of the progeny atoms in there. The ones that don't decay, they're called inert or stable. And the ones that do decay spontaneously, all by themselves, in fact, there's really nothing you can do to stop them from decaying, those are called radioactive. So there's nothing magical about the word. The alphas, betas, and gammas, as you can see here in this drawing, have different abilities to penetrate material. The alpha particle, that is pretty large, carries a modest amount of electric charge, and because of that, it can't penetrate even the surface skin in your hand. So you would think, well, that's kind of nice because if it can't penetrate my hand, it can't do me any damage. And it turns out that's exactly the reverse. And I'll get to that. The betas, these are really just electrons that are given off by the nucleus. And we call them betas. They're really electrons, but we call them betas so that we will remember they came from a nucleus and they didn't come from the outer portion of the atom. And then gamma rays, well, they're a lot like light. And they can penetrate most anything with very little interaction. If you want to interact with a gamma ray, you really have to take special actions in order to be able to detect gamma rays. Now, I want to talk about the half-life and the term half-life. There's nothing magical about the term half-life. It is, as you see here, it is the time it takes for half the atoms to decay. Now, radon has a half-life of approximately 3.8 days. And that means that if I were to put 1,000 radon atoms in this jar and I came back 3.8 days later, there would only be 500 of them. And if I came back 4 days later again, for a total of 8 days, there would be 250 of them left. Etc. And that's what this graph here is trying to show, that if you start with 1,000 atoms initially, that after about 4 days, really that's almost the half-life of radon, you've got about 500 atoms left. If you wait for another 4 days, a total of 8 days, you'd have about 250 of them left, etc. And they decay down till they get to very, very small numbers. The progeny of radon, after the radon atom decays, gives off alphas, betas, and gammas, you'll have other atoms, and most of them have much shorter half-lives. Most of them have half-lives in the minutes and seconds, so they decay pretty promptly right after the radon does. And that I'll make a remark in a little bit, will be important to us in understanding this. Now, the unit that's used is the picocurie per liter, and while I did cover this in the first video, I'll make a remark about it again. And when I say a nuclei explodes at a given rate, what I mean is it decays at a given rate. So radon decays at the rate of 50% of them every 3.8 days. Now, the picocurie per liter is a clumsy unit. And the U.S., frankly, is one of the few countries that still uses that unit. It's an old unit. The newer unit is called the becquerel per cubic meter, and actually I'll make a remark about that in a minute. But it's not particularly important to us, I don't think. Now, what I want to talk about this is, you'll see I've got here in the slide, 1 picocurie per liter is 2.2 disintegrations per minute per liter. And what I mean by that is, let's suppose I could see each radon atom and I could see when it decays. If I look at this in this 1 liter bottle and I saw 2.2 decays per minute, now, I don't know how you get 2.2 decays, but let's say 22 decays in 10 minutes. The average would be 2.2 decays per minute. If I were to look at that and I could see on the average 2.2 decays per minute in this 1 liter bottle, assuming I can see them all, then we would say that's 1 picocurie per liter. So hopefully that gives you a little bit of a physical handle on that particular unit. Now here I'm going to show you a relatively recent display of the doses that you get as a human. I'm going to enlarge this here for you, and I think I can move this down so it's a little more legible. Right. And you'll notice here there's all kinds of radiation exposure. There's some due to your job, some due to because of industry. There's consumer radiation you're exposed to. That might be, for example, if you have a smoke alarm that has a small radioactive source in it, et cetera, et cetera. And terrestrial, because the Earth is radioactive. There's some radioactive material in the Earth. Obviously, we find radon down there, and there's uranium and radium and a lot of radioactive materials down there. So you get a little bit of a dose from that. You get some dose internally, and that's because your body is radioactive. So you get some internal dose. You get some dose from outer space that comes and strikes you here on the planet. And you'll notice radon and thoron. And I'm going to group that all as radon, which is a very good representation. That's about a third, 37% of all the exposure you get on these are actually calculated from a yearly basis. And the point of all of this is that the radon, the reason I'm showing this graph is the radon is the biggest exposure that you get on the average. The Surgeon General has made the remark, and this is stunning the first time I heard it, but is clearly true. Radon is the second leading cause of lung cancer in the U.S. today. That's a pretty significant remark, I think. Now, we're going to talk a little bit about lung cancer. Lung cancer, first of all, it's not immediate. The cause of it doesn't cause the lung cancer in a few hours or even a few days or a few months. That is to say that if you were to smoke a pack of cigarettes today, doesn't mean you come down with lung cancer tomorrow. That's not how it works. That is also true with radon. You can be inhaling radon, and it can be decaying in your lungs, along with its progeny, of course. It can be decaying in your lungs, and that's not going to give you lung cancer tomorrow. It takes typically years for this kind of effect to occur. And just to discuss what cancer is, as a very general overview, your cells have a lot of atoms in it, and they have a lot of molecules in it. And some of the molecules are called DNA and RNA, and I'm sure you've heard about those kinds of molecules. And the information in those cells regulates how rapidly that cell will regenerate. And the typical regeneration times for cells in your lungs, they can be days, weeks, months, and years. But that cell knows somehow how often it needs to regenerate. Now, if an alpha particle comes along and hits that cell, unfortunately, because the alpha particle is short range, because it's big, can't penetrate very far. It will deposit all the energy it carries into that cell. And that energy is what does the damage. If the DNA is upset, then the information it contains on how fast to reproduce can change. So perhaps let me just take as an example, let's say the DNA has in it the information that, well, we need to regenerate every day, once a day. And now we have an alpha particle damage and it changes the period at which it's going to regenerate. Maybe it's going to say, well, now let's regenerate every 2 hours. Well, you're going to get a lot of cellular growth there. And if the original cell is damaged in such a way that not only is the period of regeneration changed, but the formula for regeneration changes, now you're going to get a lot of cells that are not like the original cell generating rapidly. And we call those tumors. And that's how it occurs. That's how the health risk occurs, as a general overview of that. Now, I mentioned here in the third bullet that the health risk or lung cancer depends on the radon concentration multiplied by the amount of time spent in that concentration. Now, that's not the exact formula, of course, but it is a representative part of that formula. And that is, let's say there's a radon concentration in a closet of 100 picocuries per liter. And you never go in, you go in that closet 1 minute a month. And that's not much of a health risk because the time of exposure is pretty small. Your health risk would be much greater in a 2 picocurie per liter concentration if you're spending 300 or 400 hours a month in that space. So it's the concentration and the time together that produces the health risk. And I made comments about the radon progeny, the residual atoms. They contribute significantly to that health risk. And I show you here this slide, which lists a bunch of phenomena, leukemia, lymphoma, lung cancer due to radon, etc., and the number of fatalities that they face, that they produce on a yearly basis. So radon, the estimate for radon is 21,000 deaths per year due to radon. You might take lymphoma, almost the same number. Leukemia, almost the same number. They're both a tad more, but you can see all the others are less than the health mortalities due to lung cancer. So I'm putting this here just to establish a perspective that radon is in fact a health risk, and it's on the order of other significant health risks. I show this slide to underline the concept of straight line, no threshold. And what is meant by that is that if you're exposed to a certain amount of radon, let's say you're exposed to 1,000 picocuries per liter of radon, and you're able to reduce that to 500. Well, of course, the health risk is going to go down. And if you reduce the exposure from 500 to 250, the health risk goes down further. Now I go to 250 to say 100, and then to 50 and 25 and 4. Down around 4, the health risk is going to be much less than the health risk when you were exposed to a concentration of 1,000. And let's say we lower the radon concentration to 3. Is that less health risk than 4? And the answer is yes. In fact, is there any value below which the radon is not a health risk? And the answer to that is no. No matter how small the radon concentration is, there's going to be a health risk to you. That's the way the data is showing up. Now, there's a number of studies that could be cited that underline this, and I've chosen this one. It was certainly one of the early ones, and I've gotten acclimated to it a little bit. And I'm going to enlarge the graph a little bit for you so we can see that a little better. And you'll notice here, these points, they represent the data points. And on this graph, we've plotted the radon concentration. Now, it's in becquerels per cubic meter. Now, that's the unit that's used almost worldwide. And it converts this way that 1 picocurie per liter is about 37 becquerels per cubic meter. So on this graph, I've indicated where the U.S. action level is, which is 4 picocuries per liter, or about 148 becquerels per cubic meter. Don't get hung up on the units. The point of this slide that I would like you to get is that as you lower the radon concentration, the health risk goes down, and it goes down linearly. But there is no value below which the radon concentration is not a health risk. Now recognize that you probably will not be able to get the radon concentration in a home down below 0.4, 0.5 picocuries per liter, simply because that's what's in the outside ear. And so we can try to get it down certainly below 4, and mitigators can certainly do that. And in many cases, mitigators can get it down less than 2. But to try to get it down below 0.5, 0.6 would really require some very expensive superhuman efforts, simply because that's the outside atmosphere. Okay, now let me just there we go. Now, how do we know the health risks due to radon? Well, we can look at the radon and we see the alpha particles that are given off. They're the predominant health risks. And we know how much energy they carry. And it's the energy that does damage. So we know how much energy the alpha particles carry. We know how rapidly they come out. That is, how many come out per minute from a given radon concentration, because we know the half-lives. And we can come up with a real good estimate of how long you're exposed to it, how long are you in that environment. And so we know the radon concentration, we know the amount of time, and from that we can calculate the health risk. That is, in effect, the probability of coming down with lung cancer over 10 years, 20 years, 30 years. But we also have other data, and here I'm going to talk more in general about radiation and its effects. How do we know that radiation is unhealthy for us? Well, of course we do know that. We certainly know that large doses, as you note here from the first, let me just get to that, from the first bullet, when Hiroshima was bombed with a nuclear bomb, we know how many people died between 0 and 1,000 feet, between 1,000 feet and 2,000 feet of the bomb location, of the explosion location. We know that. We know the percentages of those people. That is, 95% of the people in this range died from radiation. And as we go further and further, we know fewer people died from it. And then we have additional statistics to that. So we have that information. We have people who were treated with radiation therapy. This is part of the nuclear medicine issue, and that is nuclear medicine, which in principle is simply the injection into a human of a little bit of a radioactive material, often called a radioactive seed. We can put that next to a tumor or in a tumor, and the radiation that comes off of it, the alphas that come off of it, and the betas and the gammas in some cases, but we got to pick the right nuclear material, and we put it in there, and we know it'll kill all of the cells in that tumor. And so that's one part of nuclear medicine. And we know how much of an effect it has. Actually, we know that incredibly well. We know just how much material to put in and how long it'll take for it to kill that cell. You may even know someone who's had nuclear treatments in hospitals. I have had it. And so we know, we have very good information in that regard. In particular with minors, there has been a study accomplished. It was very thorough, very elaborate, lasted a long, long time and looked at the impact on minors due to radon. Now, this was a difficult study that was done, and very elaborate and very highly respected study, to identify the effects of the radon on the miners' lungs. And it was difficult because there are a lot of other things going on in the mines besides radon, and those have to be weeded out, divided out, subtracted from the effects and impacts of radon itself. So that's a very elaborate study. And that one I make reflection to because that was specific looking at miners and the effects of radon on miners. And then we have workers. We have this data. This is in general for radiation in general. Workers painting watch dials. You might remember, if you're old enough, you could buy a watch years ago that glowed in the dark. And what was done in order to make them glow in the dark was radium, which is a radioactive material. And when radium decays, by the way, it produces radon. That's where the radon actually comes from, is from radium decaying. But when radium decays, it gives off a little bit of visible light. Now, that's not exactly true. Radium itself does not give off the visible light, but the radium paint, so radium, that radioactive material, mixed in with some other materials that are caused to glow because of the emissions of radium, that's what we see as visible light. I'd call it the radium glows, but that's not exactly correct. It's the radium paint that glows. And you used to be able to put that on watch dials, and you could see your numbers and the hands of the watch glow in the dark. And how do you get these fine painting lines on those dials is you dip your brush, you put it on you wet it, and then you dip it in the paint, and then you can put a real fine line. And this was done by in the early 20th century, 1910, 1920, that became very, very popular. And interestingly enough, women did this. The preponderance of people doing it were women. And I have a photo here, which I can enlarge for you and get that a little better picture for you. There we go. And you can see that all of these painters were painting these radium dials by doing the lip, dip, and paint on the dials. And these workers came down with all kinds of cancers on their lips, their tongue, all over the place. And it was due to the radioactivity of the radium. So we really do know well what effect the radon has on human health. Thanks for watching this video.